Alright, hi guys. So today we're going to talk about normal and reactional forces that are acting onto two separately so two objects has been separated. So as we know, according to Newton's second law of motion, every reaction has an equal and opposing reaction of equal amounts, and has what we known from the study of statics is that if I have a flat ground, and if I were to put a box onto the flat ground and it weighs uh, m kilograms, so it has exerting a force of mg, therefore it has an equal and opposing force of n. Therefore we would know that n is equal to mg. So now what if it comes to the case of I have the ground and I decided to separate these two free body diagrams into such way. So what we usually do is that we would say that there is an mg that's going here, and hence we have an equal and opposing force onto the box that is equal to n, and onto the ground it exerts an equal and opposing force of n. There is no mg here, but we have n. That is how it is. And one of the questions that I would like to practice on in dynamics is this question. And this question was actually given to me by one of my professors, and I think it's a really good question, and I really like it because we will be dealing with moments of inertia, and we have a rotating sphere with a relative velocity and its leading acceleration, relative movement. So first of all, to start off with this question, we're gonna read the question. It says here: a cylinder of mass m, a lowercase m, of radius r, and a mass moment of inertia of jc, rolls on a wedge of mass m, capital M mass, that is sliding on the inclined plane on the angle beta. The coefficient of sliding friction between the wedge and the plane is mu1, and is sought for the wedge acceleration a capital M, the acceleration a capital R of the cylinder's center of gravity moving relative to the wedge, the angular acceleration alpha of the cylinder, the contact forces between the wedge and the plane, as well as between cylinder and wedge, and the necessary coefficient of static friction mu 0 2 between cylinder and wedge. I would probably say that this question wasn't really phrased very well in English, probably because it was translated from German to English, but no worries, I'm going to explain this. So the first question says, draw cylinder and wedge including all dynamic loads. So one of the ways that we're going to draw this, we're going to cut in between here, and once we cut in between here, we're going to have two separate bodies. So the first body is that we're going to have a circle, the wave itself, with the circle, and in this circle it rotates in this direction of omega alpha, as is stated here, and we know that it has a moment of inertia, so it's going to be js alpha, and we know that from the center itself it's accelerating to the right, so it's ar. So we know that in opposite direction we have an inertia of m a r, and of course we do not forget that it has a mg, and in response we have a n2, and since we have an n2 here, because it's accelerating to the right side, it means that its friction and it's rolling to the right side, therefore its friction is going into the left side. So I'm going to call this R2. I think I'm going to call it FR2. I like F better just to remind us that it's a force. And the first free body diagram. The second free body diagram is going to be the slope of the wedge. So you have a wedge like this, And here we're going to say it exerts a force downwards, which is a capital mg. It also has reactional force that's exerting onto the slope, which is I'm going to call n1. And because it is going in this direction, sliding down, we're going to say that it has also a inertia of capital M A M. And another thing to remember is that because it's sliding from the right to the left, we have a reactional forces happening in the opposite direction, the reactional frictional force, which I'm going to call FR1. And as you remember that because in the beginning we had N1 is this direction, that proves that we also have N1 that's going into this direction. N2, yeah, N2, sorry, not N1. And because we have frictional forces going that direction, let me color this with what's called purple. Therefore, this proves that we also have a equal force in the opposite direction. So you need to always remember that they are in opposite directions when you are separating the bodies. Now, as you need to remember that because this whole thing is sliding downwards, and because this thing is gonna roll to the right, whatever that is happening here also happens here, but whatever that's happening here does not happen here. So I'm gonna highlight this as blue. If this is an acceleration AM, it means that we also have an acceleration in this direction called AM, but we do not have AR here because it's not influenced by it. So you could say that the circle is influenced by the triangle, but the triangle is not influenced by the circle. And last but not least, you have your angle beta over here. And this is your cylinder, dynamic loads of the cylinder and the wedge. Now to formulate the 8 equations, can I bring this both here? No, I don't think so. So for your first one, as we know that FR2 is equal to mu 0 to N2, and we know N2 is equal to I would technically say N2 is equal to mg plus I forgot one important thing, which was that you have to write this as well, M A M. I'm just gonna highlight this to remind ourselves. Plus M A M and because we know that the angle here is beta, therefore we can say that the angle here is beta, which is then here, which is also beta. So we have M A M we're pointing this vertically away from the angle, so we're going to say sine beta, and then the horizontal one would be, this is your vertical, and your horizontal will be MAR plus FR2 is equal to, sorry about that, is equal to MAM cos beta. And I'm going to call this point C. So your moment at C, and as you remember that the radius given to us is R, and R is equal to, no, R, we're not given R, okay, this is fine. So at C, you would say that JS alpha is equal to FR2R. Draw a line here. 1, 2, 3, 4. We have 4 equations there. We need 8 equations. We need 4 more equations. So for here, the basic one to know is that we're going to say FR1 is equal to mu. I think there's no mu. It's just called mu1 times n1. And we know that n1 is equal to mg, and the angle is going to be, here is also beta, so it's going to be mg cos beta, yeah. And for the vertical force, that was the vertical force. Wait, sorry, I made a mistake. So basically, yeah, it's true. N1 is equal to mg cos beta plus N2 cos beta plus FR2, and we're gonna tip this angle, so it's going to become sine beta, because if I draw a line here like this, we know that here is beta, so to move this to this direction is going to be sine. That's why it's sine beta, yes, and that is your n1, and this is in this direction. I mean, it's not really good looking, but it is, yeah. So now we're gonna solve it in this equation. From this equation, we say MAM is equal to MAM. What else is going in that direction? Apparently, we only that was we have also plus FR2 cos beta and equal to N2 sine beta and plus N1. No, N1 is not in that, it's in opposite direction, wrong direction. Plus mg in the sine direction. Yeah. And I kind of forgot one more, which was to put in FR1. Yeah. And I forgot so we have 7 equations here, so what else do we need? We need 8 equations. Okay, so I forgot one more, which was the 8th equation was AR is equal to R alpha. And the reason for this is because the whole entire thing is translating from the left to the right. So you could say your AR is the same as equal to your tangential acceleration, which is y is equal to R alpha. So therefore you have now 8 equations in total. So you have 1, 2, 3, 4, 5, 6, 7, and 8.